Hi, this is my review of my summer internship at ASEP on the Demand Response Emulator project, and I'm Samantha Feemster. Demand response refers to enabling the control of some consumer loads in an electrical system in order to reduce or increase total power demand, thereby optimizing the utilization of power generation assets. There are two main types of demand response: dispatchable and non-dispatchable. Dispatchable demand response may refer to a utility billing system similar to Uber's variable rate system. It is more expensive when people are using it, simply put. Direct load control is a form of non-dispatchable demand response. It is already common in California and similar climes where central cooling is prevalent. Utilities there offer a discount if customers opt to have a black box installed in their AC unit, which allows the utility to switch off power to their AC whenever it suits the utility. Researchers are looking for more ways to incorporate demand response in residential markets where AC units are not the largest load in a household. Direct load control for clothes dryers, water heaters, and refrigerators, for example, would require either their manufacturer or the owner to incorporate external controls to allow remotely switching these loads on or off. One of the main benefits to demand response is peak load management, meaning it can lead to a reduction of the peak load. So if you go to a gym, you're familiar with peak load time. It's from 5 to 8 p.m. at the gym featured on this graph. Many people simply go to a gym well before or after the duration of peak usage. Peak load management refers to a similar change in behavior. An example in power usage would be a building pre-cooling before peak load times, so from about 2 a.m. to 9 a.m. according to this sample graph. Demand response can also increase grid stability by controlling which loads are dropped in the event of generator overloading and a reduction in frequency of the power generated. If you think of a generator as a car driving uphill in a high gear and the grade of the road as the amount of power being pulled by the connected components, then direct load control allows for a fast reduction in steepness of the road so that the car continues after slowing down rather than stalling out on the hill. In the case of a diesel-electric generator, sustained overloading will result in a blackout. Demand response may also decrease losses by decreasing the overall expenditure of electricity, automating the dimming of lights after hours or adding motion sensors for lights in rooms with periodic use, for example. I was tasked with designing a profiling setup for the Saturn South devices with direct load control capabilities in order to facilitate the construction of an accurate simulation of a fleet of such devices. We are currently gathering data on the total time for command processing and the time from a command being sent to when the switch on the CT meter actually opens and cuts off power to the load, similar to the AC unit controls I mentioned earlier. Below is an example of one of my drawings for the initial setup. I also helped to start designing a proof-of-concept demand response emulator for ASEP's lab and researched a number of topics related to demand response. Saturn South's 120AR mini CT meter and the ES-Box LT are the components used in our test setup to enable direct load control. The mini CT meter records multiple characteristics of a circuit, including the frequency of power output by a generator or utility, and the current flowing to the connected appliance, or the load. The ES box connects multiple CT meters via a Zigbee network, similar to Wi-Fi, and can interface with a local network to send data and receive commands securely. A switch in the mini CT meter disconnects a load from power when either the utility-supplied power drops below a specified frequency or when given a command via the ES box. This project could serve as a proof of concept for the Saturn South components' use as direct load control devices in North American residences. With more work, it could lead to a field test where there are multiple mini CT meters on multiple loads in multiple homes, all connected via Zigbee by their respective ES boxes, and connected to a single server hosted on a BeagleBone on a local network issuing commands and gathering data, because every household should have a BeagleBone in it. I just want to thank my advisors and coworker, Dave, Louise, and Mark, and Alana for all the time and help they gave me throughout the summer. I really enjoyed working with such cool and complex components and with the ASEP team.